Good to see you all joining us. Zachariah. Fintar, I can see his typing. Hopefully that's a thumbs up. Great stuff. Okay, we will be gentle. We break networking because networking can be kind of complex and it kind of can blow a few people away. We take you gently into it. We're going to do an introduction to networking, which will take us through some of the basic concepts of networking. And then we expand on that idea of networking into some of the more in-depth properties. And then we finish off basically with a whole lecture where we also do troubleshooting for networking. So for those of you who have done networking, this is probably quite some simple stuff, but let's go through it so we all understand the basics and we all kind of start from the same sort of level. So we're going to talk about, as I said, the basics of networking. So understand what a basic network is, the concepts, the technologies, and their significance. If you are at all confused, this session is one to be asking questions. Okay, please feel free to dive in, poke me with some questions. If you don't understand, there's different ways to explain the variety of networking concepts. I'm very happy to diverge off. So I'm going to talk about things like LAN, WAN, and MAN, and it all makes sense when we come through to that. And we're going to talk a little bit about some of what we term as topology within networks, as well as protocols, devices, and services. So we are going to cover quite a fair bit today. So fundamentals. Okay, basic definition of a computer network. Okay, it's a computer network is a collection of interconnected devices. They don't have to be servers. They don't have to be PCs or anything like that, such as computers, servers, routers, switches, or other hardware that are linked together to facilitate the exchange of data as a resource. So networking is basically definition of that. Other computer devices working together, we talk about network. So a networking is what we're kind of physically doing. A network is the physical structure. Within those networks, we will talk about things such as routers. We will go into some detail about that as we go through. And switches and what the difference are between routers and switches. We'll also talk about LAN. LAN is a local area network. Put your thumbs up if you've heard that term before. I'd imagine most people have. Marcos definitely in there, thank you. Yeah, so loads and loads of people I can basically see coming in there with, yes, you've heard of the term LAN. That is fantastic. And who's heard of the term WAN? So LAN is our local area network, basically in our building. WAN is going to be an expanded side, so it's a wide area network. And we talk about the definitions between the two of those. See loads of you typing thumbs up in there. And we're also going to chat about IP address. So what is an IP address? What is IP4? What is IP6? How do we manage IP addresses and what indeed do we look at? So we'll basically deal with that. And we're going to have a little chat about DNS, which is domain name services, and exactly what DNS does for us. So why is networking so important? Okay, it obviously plays a pivotal role in sharing data. Before we had networks, you had to send things like carrier pigeons around or pieces of paper. People running backwards and forwards, passing information across. Networking allows us to share data. Internet access allows us to build much more into a communications device. So we're not just now basically sharing bits and data, we're turning into a full-on communication devices. And it means we can store our data whenever we like or wherever we like. We're dealing with a network. It's not important how local it is anymore to us. It's just important that the data is stored somewhere. We will talk about the importance of it being fairly local for speed issues, but data storage and remote access. So we can access data from wherever we are now because of the beauty thing called networking. And within the networking that we have nowadays, it is infinitely scalable. We are not stuck with just, oh, it's just our small little group here. We'll attach one or two other systems to it. It is massively scalable. So you can go from a nice, friendly local area network that you sit at home with into a multinational corporate environment. And the concepts behind it are exactly the same. Obviously, it's just a bit bigger. And within networking, of course, there's a big importance for centralized management systems and global connectivity, and we'll go into those in some details. So physically, what are networks connected with? cables. Most of them are cables or Wi-Fi, radio signals. So networking connection, cat cabling is probably one of the standard ones. Okay, cat cabling. I've got some cables somewhere. I'm sure you've all basically seen cat cabling. Hold on. I feel bad if I don't show you a proper cable. Okay, so cat cabling, it's a good old stuff that we're basically very familiar with, that we probably got in our house and we've seen all over the place. They vary in speed. Okay, cat 5 is up to 100 megabits per second. Cat 5 is up to 1000 megabits. Cat 6 is, again, is 1000 megabits. Cat 6E is 10,000 megabits per second. So you can see we are increasing the speed with the quality of the cable. That's what drives the speed difference between those. Fiber optics, which is our super fast network. So the ISP will basically give you 10,000 megabits per second is what you can do. Theoretically, and no one's basically used this before, is theoretically we can go up to 44 terabits per second. Okay, which is an awful lot of data. Okay, we're not using that at the moment, but yeah, most ISPs will max out about the 10,000 megabits per second. And then, of course, if we don't want to plug in a good old-fashioned cable, we can use radios. We can use our 4G and 5G networking. Difference between 4G and 5G. 4G was 150 megabits per second. 5G, you can get 10 gigabits per second. Okay, so radio is very happily catching up. Any questions about the types of cables? Good stuff. Okay, there are other cables that we'll probably talk about when we do the more advanced stuff, but these are really what we're talking about here is most of our networking cabling and structures. So we know we can also communicate across Wi-Fi. Of course, the radio one that we're talking about, 4G and 5G, that is for wide area stuff. So we are literally passing signals from our phone, from our laptop across to a mast that could be 2-3 miles away. And that's basically how that works. If we're doing more local stuff and we're talking about our local area network, our LAN, then we're going to want to use Wi-Fi. Wi-Fi currently comes in 2 particular flavors. Okay, there's a 2.4 gigahertz, which is the radio wave that's basically used. And that's good. It's slightly slower than 5 gigahertz, but it's got a better range. Okay, so it's larger ranges, slightly slower speeds. On the right hand side, you can see some columns there. Okay, the protocols, which is basically the language that it's talking, will control the speed that you can get up to. So the good old-fashioned legacy, you can see the 802.11, 802.11b, 11a, 11g, etc. They will give you different speeds depending on what frequency you're using, or whether or not you're actually running at 5 gigs or 2.4, and that will again will affect the speed that you can get up to. Now, you won't need to know all the actual details for this for your exam, but what you need to know is that there is a difference in range for 2.4 and a difference in range for 5. And the speed differences are there as well. But you don't have to be able to quote the speed differences. Ballparks is probably good enough for a lot of this. So say, please feel free to ask any questions. So we can either link up with a physical cable or we can do it on a Wi-Fi network. Good. So to make cables, we can use tools such as crimpers and punching tools. Okay, these tools are basically designed to allow us to make cables up. So they don't always come with the very attractive ends on. We can basically just buy reels and reels of them. I've got a 100-meter reel somewhere hiding around up in my loft that I use because basically I ran a set of cables down to my garage. Okay, so it's as simple as that. You can basically make your own, and this one has some terminators here, and they're fairly similar. If anyone's basically used, I was just about to throw into something like a PSTN line. PSTN line is your old telephone line. Okay, so it's very similar to crimping and doing the work with a telephone cable, same as network cabling. And then we have some other crimpers. So the crimper set on the left-hand side is basically designed to work with, that will work with our PSTN line. So it works with our Cat 5 cables. And the one on the right-hand side is really for fiber optics. So we can make cables up as we like. You don't need to know the cable combination in terms of where the red one goes, where the brown one goes, where the blue one goes, where the green one goes. what you need to know is that you can cable them up yourself. Anyone done any cabling themselves before? Let's have a thumbs up for anyone who's touched any cabling before. If you haven't, that's perfectly okay. So it looks like Peter has. Well done. What were you cabling, Peter? Was it a Cat5 cable, or was it some fiber, or was it something else? I see a couple of you typing in there. I'll give you a second. Or if you stop typing now. Okay, we'll just carry on. That's fine. So those are the cables. Got no questions about the cables? Then let's drift on to, I tell you what, let's go back to cables. What's the big difference between a Cat5, a Cat cable, and a fiber optic cable, other than speed? It's one of those weird questions I tend to ask people. These Cat5 cables are copper, okay? So they're beautiful copper cables. Yes, we shouldn't really do a lot of this, but we can do. Okay, they're quite flexible. We can tie them in knots. We can do a little bit of things like this without any problems. You wouldn't do that with a fiber optic cable. So a fiber optic cable is really, it's like a glass pipe. It's a finely blown glass pipe. And the speed and the reliability of that glass pipe depends on not having as many cracks in it. So if you do that with a fiber optic cable, you are introducing cracks in that glass cable. And that basically depreciates its efficiency. So with fiber optics, you tend to be a little bit more careful with what you're doing in comparison to your regular network cables. Fiber optics is also used for longer distances. Paul Bird says reliability. I'm not sure that's quite true. I'd certainly pick a network cable over something like a fiber optic at times, but it depends on the distance. So fiber optics, faster and longer distances than our Cat5 or Cat6, Cat6e cabling. Okay, so let's literally have a look at some business context. So let's explore our small office network. So within what we have as our small office network, we would have something that's known as a ISP router or a modem. We've all got one of these at home. We have an internet connection that basically the ISP router connects through to our internet service provider. And then we have a local area network. And we'll show you where they all sit later. We then have what is known as a private IP address. Now we're going to talk about exactly what IP addresses are, but this is a bit like being inside our house. So everything inside our house tends to be in our LAN, which is our private network. And that has its own IP address. Whenever we talk externally, we talk on what's known as a public IP address. And I'll go into some more details later about that. Let's skip over it now for the starters. Then in the small office, we basically have some network configuration, which controls what can talk to where. And of course, we can introduce our Wi-Fi systems onto there. Along with that, of course, we need security. So we need something like a firewall that's basically going to look after our security, or a router that's going to handle who can talk to who. And then we have what's known as IP support. So small office network then. So we have many devices connected via cables, via Ethernet ports or other cables. We have something that's known as loop prevention. Now, loop prevention means that you will not get a system that talks out and then responds back to itself. It's quite important, but not that detailed. We need to go into that much detail at the moment. Okay, so loop prevention is something that's built into most modern systems. A lot of it is plug and play. You simply plug in your network cable into the devices and you can basically spark it up and it should talk to each other. Already mentioned the ISP router, scalable. How many devices can I plug into a local area network in a small office? Does anyone want to have a guess in live chat to tell me how many devices I can plug in to a local area network? Anyone fancy a stab at that one in live chat? Guesses are good. I like guesses. 5, says Marcos. 12 is Ronald. Any advances on 12? I like this. This is great. I can play 40 questions. 50, depending on the router, maybe. Sebastian, is there a cap or is the maximum the router could support? So Sebastian wins a box of sweets today then. Yes, it's basically your local area network can be as small or as large as you want. We've all got essentially a local area network at home, haven't we? So we've all got a router that's provided by our internet service provider that connects out to the internet, and we'll talk about how these fit in. The amount of devices you can connect to that ISP router is really totally dependent on how you want to build it. If you want to basically connect 200 Wi-Fi devices to it, if that router supports 200 Wi-Fi devices, yeah, you can have 200 Wi-Fi devices. Chances are it's only got 4 cables sockets on the back, so you'll probably only be able to physically plug 4 cables in. But as you can see, we can expand it as much as we like because we can put another switch on the end of it, and then we can expand it even further. Bandwidth, as Sebastian mentions there, is really where things start to slow down. And we'll talk about that later. So we have management options, which is where we control our network capabilities and what we are moving around. So how does a local area network look? Here's a small office network. I've got 4 PCs. The blue lines are basically network cables. So I've got our physical network cables plug from our systems, and they go into what's known as a patch panel. So a patch panel is a dumb panel. It doesn't do anything. It is like a straight through connection. Okay, and then that patch panel will basically have connections that go through to our switches. Now here I've drawn 2 24-port switches. So there will be a patch panel cable that goes for each of those devices into those ports, simply linking it up so those devices are now connected directly to a switch. And then that 24-port switch, as you see, has a connection to the second 24-port switch, and that 24-port switch has a connection directly to the router. And then the router connects out to the internet. So every time I look at a network diagram, if I can draw a line, a direct line, from a device at one end, from, for example, the printer, and that line can trace through a network cable to my switch, my patch panel, then to my switch, I can draw a line to my switch, and then I can draw a line from my switch to my router, and then I can draw a line from my router to the internet. That device, we can probably say, and there are lots of exceptions, that device will or should be able to connect to the internet. There are some caveats, and we go through a lot of that when we talk about it. But in terms of physical connections, if there is no physical cable between the patch panel and the port switch for that printer, then that printer won't physically be able to connect any further. If you watch any movies, that's what they call air gapping. My friend used to like that idea for security when he started doing his security job. He said the best defense against security breaches was an air gap. And he demonstrates that with a pair of pliers, just cutting the cables. And that's what he likes for his security. Okay, so is that clear to everyone? Literally, we are tracing physical cables. We do a lot of the background, and the software end would handle a lot of the other stuff like IP addresses and who can reach what. But if there's no physical connection through, then you are not going to get any data down that line. Now, of course, everyone's screaming at the screen going, oh, what about Wi-Fi? Okay, so Wi-Fi, essentially, we look at it and we go, that essentially pretends to be a physical connection between that device, although it is coming through the radio. There's a connection from that device, potentially to a router that then connects further on. But let's focus here on the physical cable end of things. So has anyone got any questions about that simple, small office network? So I've got a question for you then. So what other items might be incorporated into a small office network? What other devices might I include there? Printers, yes. Marty, Ronald, well done. We have printers in there. Bluetooth devices. Bluetooth tends to connect not via a network, though, is it? Bluetooths are basically connecting to a device. So you connect a Bluetooth phone to a set of speakers, or you connect a Bluetooth device to your PC or your laptop. Don't think of Bluetooth so much as straight networking, but potentially, yes. Devices that might pick it up. Security cameras. Marty, perfect. Security cameras. Yes, our security cameras nowadays run off of IP addresses, don't they? They run off our TCP/IP network. So yes, they definitely would connect into a small office. No reason I shouldn't have a security camera in my small office. Phones, yes. So Chris mentions phones there. Yes, phones we basically connect via our network. We do what's known as voice over IP, which is VoIP, which means we no longer carry our telephone voices via what was the old-fashioned PSTN analog line. We basically can carry it over data, which is VoIP, and we go into that in a bit more details when we talk about the advanced stuff. Brent's mentioned scanners. Yes, there's no reason you can't connect your scanner to the small office. And Sebastian there, thank you very much. Possibly a small internal server. Run on smartwatches, you're probably talking about Bluetooth rather than basically being on a network, aren't you? You just need to separate the idea of Bluetooth and networking. Wi-Fi is networking. Bluetooth is slightly different. Communicates roughly in the same way, but it isn't what we normally connect up. I can see Maximilian's typing there. While you're thinking about that, I am going to scroll back a couple and ask one quite important question. Why have I put two 24-port switches in there if I'm only really supporting 5 devices? Anyone think of a reason I might put that in there? Just smash it into live chat. Marcos says more users can also connect. Yeah, sure. So I can expand the number of users. So in theory there, I can have slightly less than 48 because, of course, I need a port to connect the 2 switches together and a port to go to the router. Marty basically says in case of expansion for new devices, Ronell for expansion. Better not be limited and doing an upgrade later. Yeah, certainly. It's one other quite important reason there. See if anyone gets it before I tell you. Redundancy. Bag of sweets going to pull there. Redundancy. So there's an issue with one. So if I break my first 24-port switch and it goes up in smoke, my network is dead. If I've only got one there, I then have to phone up, order one. Yeah, they might do next day delivery, but probably come in a couple of business days. With redundancy, we always want to be thinking about that. 24-port switches are quite cheap devices. I say quite cheap. Yeah, they're relatively cheap. So very simply, by buying 2, if one goes up in smoke, well, I can just move the patch panel cable into the other one. All of a sudden, I've got my network connection back. And my devices are working fine. So whenever you draw a network, and whenever you think about a network, think about redundancy. I've got 2 patch panels there for exactly the same reason. So if, for example, my printer was basically plugged into patch panel 25, if 25 stopped working all of a sudden, and I think it might be the cable there, then I could probably plug it into one of the other patch panels and try using that one. But you've got to remember, if the patch panels are normally labeled on the walls, so around your office, you will normally see a port or something like that that is labeled with 24, 25, 26, 27, 28, 29, etc. And that's the one you plug it into. The patch panel cables, the ones that are drawn in blue there, normally go underfloor or through the ceiling cavity or in boxed coves around the room. Okay, so you won't normally see them. But what you do have is you'll have a label at one end that tells you it's port number 17 And then you know in the patch panel that is port number 17. And that means you can plug a cable from there to your switch and you go, well, I've now connected port 17 through. So I can now plug my printer into port 17 and then I have the full loop all the way through to my switch. Does that make sense for everyone? Let's see. Who's ready for Kahoot? Thumbs up if you're ready for some Kahoot questions. Great stuff. Sebastian, Ethan, Marcos, that's fantastic. I'll give a couple of you a bit of time just to quickly join and get onto the Kahoot session. You're having trouble, let us know. Paul Bird, you just love Kahoot, don't you, Paul? If you keep winning though, Paul, I'm gonna be forced to work a way to get a handicap on you for the Kahoot quizzes. Okay, so we've got 19 of us ready. Let's kick off Kahoot. Remember, it's only a bit of fun. Fastest fingers in Kahoot gets the most points. So here we go. The first question is a quiz. Multi-select, so pick all that apply. Which of these is a network device? Oh, I see a couple of you pick printer. Yes, printers we connect to networks. They're very rarely considered to be a network device. The networking devices would be the router and the switch, and we'll talk about what they do a little bit later on down the line. Poor start for you, never mind. So it looks like we put Sebastian at the top. M and Max are up there. Zachariah and Fintan. Okay, let's have a look at the second question then. Networks allow for the sharing of data. True or false? Oh, a lot of fast fingers coming up there. Like you guys are getting very familiar with the Kahoot nowadays, aren't you? Let's see who basically clicked that one the fastest and whether or not they clicked it right, shall we? Ah, well done, everyone. Okay, thank you very much for everyone. Pat on the back for everyone there. Yes, they are basically designed to share data. Sebastian was quick in there. Max jumped up. One more question for this particular round before we drift on with the rest of the work. A small office cannot be more than. A small office cannot be more than. How many devices can we connect to a small office? Okay, the correct answer is as big as I like. Okay, I might pop back to that. So a small office can be as big as you like. See, remember the example I showed with the switches? I had two 24-port switches. Okay, so I can have at least 40 there. There's no reason I can't put another 24-port switch, another 24-port switch, another 24-port switch. And it can go on, and I can add Wi-Fi onto it, so they can have another 200 Wi-Fi devices connected on per router I have, if that's my router limit. So I can really make it as big as I fancy. Let's see how that's affected the scores then. Sebastian still maintains the lead there. Well done. Max up there. Really good. Well done. Okay, so we're going to drop back into the lecture. There is more Kahoot later. There's time to catch up, people. Don't you worry. So let's have a look at the types of network. So we said we would have a brief discussion about this. So the types of network, LAN, local area network. So we basically said this is purely defined by the fact it is literally in the local area. These are normally divided into buildings. You can have two buildings that are joined slightly together, and that still can be considered a LAN. But depending on whose definition you work with, that can be expanded further. So a LAN is simply our local area network. Then we have what's known as a WAN. So WAN is a wide area network. This is wide reaching. So this, don't think of this as the World Wide Web. This is my wide area network. So although some of the communication might go through something called a VPN tunnel, which we talk about in the advanced section, we are simply looking at my network. So I can connect my office here to someone who lives in Jamaica without any problems at all to their office, and it forms part of my wide area network. I can connect to an office in New York. I can connect to an office in Bristol. I can connect to an office in Dublin. So I can connect all those up, and that basically forms my wide area network. So I've got lots of different WANs connected to lots of different LANs, local area networks, connected in a big WAN. Is that clear for everyone? I'd hope so. And then what we have is we have a MAN. So a MAN is a metropolitan area network. Now, the difference really between a MAN and a WAN tends to be the distance that you're basically traveling. So metropolitan area networks are very simply within the same city. And you know full well within the same city, if I happen to be in sunny Bracknell that I am at the moment, I can physically, if I pay all the right people, I can physically run a cable from my office to a friend's house, and that will form part of a metropolitan area network because I'm not reaching out to the internet. Now I can do that same concept with a WAN, but a WAN I would normally go to the internet, so out to the ISP, so the internet provider's piece, which is on the internet, and then back in. Although that will be on a VPN tunnel, that still touches the internet, which makes it more of a WAN rather than a MAN, which is me physically laying the cables myself. Yeah. So as George Michael said, wham bam, thank you, man. A WAN is bigger than a MAN. Metropolitan area, I think it's just got to be in the same town. WAN, global wide area network. Does that make sense, Paul? Good stuff. Okay, so we're going to have a little look at this. This kind of covers pretty much what we've spoken about here. So a LAN tends to be in your office or your home network or an educational institute if you're at colleges. So the key characteristics are this high data transfer rate, because literally I'm running everything directly through a fiber or through my cat cabling. So we've got a high transfer rate. We've got low latency because we've got a short distance. Longer the distance is, the higher the latency you get. Typically privately owned, so it's owned by me. It's my local area network. And the common technologies that we use on that are things like Ethernet and Wi-Fi. When we move to being a MAN, we get metropolitan. So this is a city-wide connection. A good example there, it could be interconnecting of a data center. You may have a data center in New York West and a data center in New York East, and you connect those up, and that basically forms part of your MAN. Sometimes it's used by telecommunications provider. Key characteristics are they tend to be a higher transfer than WANs because we're not going to the internet, but they tend to be a bit slower than LANs, depending, of course, on the cabling and the facilities you use. They can be privately or publicly owned, so you can share these as well. They tend to be private is what I tend to use them for rather than anything else. And they can use a variety of transmission medium. So they can include fiber optics, wireless technology, and other things such as that. And of course, we'll chat about our WAN. So WAN is the larger coverage, interconnected LANs. So each individual LAN will connect and make a big WAN, basically when they're all connected up. Global connectivity. We don't care where in the world you are. For a WAN, we should be able to connect things through. There's a longer transmission delay simply for the distance. You know, we are passing electricity over these distances. Longer distance will take a little bit longer. I know we are running literally at the speed of light at times, but there's obviously a longer delay. They use various technologies. Yes, we can use these as a satellite link to basically do these things. Public internet connections are often used, so we can basically go out via the internet. It tends to be via the internet via what's known as a VPN, which is a secure tunnel from one site to the other. So in theory, it shouldn't be intercepted. In practice, it doesn't really get intercepted at all. And they often involve multiple service providers. So our wide area network, because of course I have to talk out to a service provider. For example, here I may be using BT. With the wide area network, there's no reason that the other end needs to be with the same service provider. I'm sure Jamaica doesn't have BT as a service provider, so they'll have their own individual service provider that connect them to the network. Starlink from Tesla? Yeah, very true. There is a fun question. I think one of you managed to answer this the other day, didn't you? I can't remember if it was this group or a different group. What's the furthest wide area network that we currently have in existence? Radio, but where do we send the radio waves to and from? I can see a couple of you typing, so I'm going to give you a minute. Definitely it's outside of our planet. Mardy, can you think of somewhere outside of our planet that we communicate with? Alan answered that. Was that a while ago? Alan picked that one up, Ronald. Thanks. Yes, I knew it was this group we had this because we've got some really bright people here. Yeah, so that is that's the furthest example of a wide area network. That's how far we are transferring things. Okay, so don't ever think of a wide area network being slightly constrained. Yes, we can have it anywhere we fancy. Beautiful work. So remember, summary, basically LANs are considered to be local. WANs are considered to be long distance, but a WAN will normally consist of lots of connections between local area networks. So it really is a way of connecting our local area networks to form a big network for us. Any questions about those two before we dive into Kahoot? Okay, let's see how our Kahoot looks then. Here's our Kahoot puzzle quiz. Put these networks in order of size, smallest on the top, largest on the bottom. I hope you're not multitasking there, Paul, typing in live chat as well as picking the answers. Hope it's not delayed you. Oh, you've done it wrong again. Paul, you're just trying to rush through, isn't it? I love the enthusiasm, Paul. Couple more seconds for those people. Okay, so that's the right way around. So LAN on the top, that's the smallest component that we basically have, the smallest network. MAN is the next step up. And then WAN is kind of the jumbo size one. Max, fastest fingers. Look at that. Max is really on a roll. Well done, Max. Let's see how the next question fixes. Oh, I think we've only got one question on that one. That's okay. Like I didn't jump to the next one. Okay, so let's have a look at the devices that we'll find in our network. We've already spoken about the cables. So some essential devices. We have what's known as routers. Can anyone tell me where their router is? You all got a router. Can you tell me where your router is in your house or that you're currently connected to? Of course, that depends where you're sat. If it's at home, you've all got one at home, I presume. Marcos is in the living room, yes. Marty, living room, behind the TV, so my kids don't find good place, Luca. Keep the kids away from it, definitely. See several other people typing. Fintan in the living room. Paul Bird. Paul Bird says table next to the front door. Not ideal, but nowhere else for it. Fair enough, it is definitely that way, isn't it? See several of you typing away. In the kitchen. Keep it away from people. I know a guy, oh, it's really weird. I know a guy moved into one of these in the UK where there's a lot of people that are converting office buildings into accommodation. I know a guy who basically had one of these properties. He got a router, fantastic cable connections coming. He decided to put it somewhere out of the way. He put it into the cupboard that was actually used for the entire building's electrical supply. So he had the main cable for the electrical supply running right next to his router. And he called me over to his house and he said, Dave, I can't understand why I'm getting no Wi-Fi signal. And I was like, it's next to this massive, great big electrical cable that's running electrical power for the entire building. Probably put it somewhere else. So other devices, switches. So our switches are basically smart devices, and we'll go into a little bit more detail about them. But what you can think about is a switch. If you plug a device into the switch, in theory, it can physically connect to everything else that is plugged into that switch. Now, there are, of course, subsections, differences in that, and indeed we can talk about routers and switches and how they basically route traffic. But if you think of a switch, if I have one device plugged into one end of the switch and another device plugged into any other port on that switch, in theory, that is then giving it a possibility of a physical connection through. So think about that when you're dealing with switches. They're intelligent because they will handle routing. Right, then we have hubs. No one ever sees hubs nowadays. They're an old feature ever since the technology got cheap enough to basically move it all into switches. Hubs are dumb. Hubs are really stupid. They are a total physical connection. So as with switches, a switch will decide whether or not your port 25 is, well, your port 24 is able to connect to a device on port 7. Your switch is intelligent enough to say, yes, I should allow that traffic. Your hub isn't. Your hub just sits there and goes, yeah, it's traffic coming in, traffic going out. That's what they do. Think of them as dumb devices. You will probably never see a hub in a network anymore. And then we have access points. Okay, so the key thing about access points, they are wireless access points. So it allows wireless network devices to connect to a particular location. What you will normally find is that your access point will then basically get physically connected into the switch or physically connected into a router. Now, you should all be fairly familiar with your access points. Where's your access point in your house? Type into live chat. Tell me if you can tell me where your access point is in your house. In the router. Thank you very much, Alan. Beautiful. So although I have literally just told you there's 4 different types of network devices, they don't have to be separate. Strangely enough, your router that your ISP provides you is also a switch because it has 4 spare sockets on the back that you can plug devices into. It also acts as an access point, a wireless access point. So that one device is carrying out 3 different jobs. And then I'm going to amaze you by saying it's carrying out a 4th job. And there's a bonus for anyone who can type me the 4th job it's doing, but we will scroll through and let that carry on through. Because I don't answer the questions I'm going to ask later on for you. Alan, don't ruin it for me. No, you can. I don't mind. Okay, thank you very much. Yes, okay. So good. So typically we have a router which is positioned on the network boundary. So routers come on the network boundary where the local traffic meets the internet. Switches are placed on the local side, and they can be placed anywhere. They don't have to be placed next to each other. You can have multiple switches throughout your building. You can have a switch on the 1st floor, switch on the 2nd floor, switch on the 3rd floor, run a cable connecting them all, and then all of a sudden you've got 3 floors that are now connected. So they don't all have to be physically located. And then you have one connection that goes to the router. Wow. And all of a sudden all your 3 floors can now talk to the router. Hubs, we said, are basically old systems. Access points, modems. Okay, modems are typically placed on the customer's premises to connect the internet service provider's network. Park modems for a minute. Don't think too much about those guys. Think more about routers. Oh, firewall. Firewall is basically placed on the network perimeter to protect internal networks from external threats. So what's the difference between a router and a firewall in terms of where we would place it? We're going to save that question. We're going to ask you. Oh, go on, Alan's going to get cracking. See a couple of you typing there. It's always good to get people feeding back like this. I like this. Firewalls face outwards. Firewalls are like the antivirus, yes, and we do go into more detail certainly when we start talking some of the advanced networking. We'll discuss firewalls in some details. But although now you can answer that other question, can't you, Alan? So where is everyone's firewall? Is one question I'm going to ask. In the router. There you go. So my device, my ISP device that the network provider has provided me, which we commonly know as a router, is doing firewall, it's doing routing, it's doing switch, and it's doing our access point. And that essentially is called a SOHO. And we talk about SOHOs when we basically do the advanced networking end of things. SOHO stands for small office home office device. We have firewalls on our Windows devices as well. Alan, we'll park that for a minute. We do go into those devices and we'll talk about that in some details. Marty asked a question. Do all routers have built-in firewalls? No, they do not. Now, this is where we get the difference between what we consider to be a router and a firewall. And we will talk about that when we talk about IP addressing and subnets, and we will show you the difference. But basically what it is your router can sit between 2 different networks. And the term routing basically means it controls the routes. So within my building, say, for example, I've got a 1st floor and a 2nd floor. My 1st floor may terminate in a router, and that router will control which traffic my 1st floor can pass to my 2nd floor. So it will control the traffic and say, yes, these devices can talk to this printer, or these devices cannot talk to that printer. And that is a router. It controls the routes of the traffic. Now, a firewall sits just before you hit the internet. So that is designed to protect all your local area network side from the big bad internet that is out there. So that's its job there. So it sits on the boundary between the 2. And indeed, for small offices where we have a SOHO device, it is exactly the same device that does both. Does that answer that question for you, Marty? Great stuff. Any questions about those devices then? Because I think probably a good thing to do is to talk about IP addressing. There we go then. Who knows what their IP address is? Good. So there's a few people who know what their IP address is. Do you know what your actual IP address is? Now, I hope we only deal with, we're really going to focus today. We're not going to talk about IPv6. We will mention it. But whenever I mention IP address, think IPv4, okay? You don't want to check IP config. Okay, so IP address. Oh, IP config. IP config is a command we're going to use later on. Don't worry too much about it. This just shows me my IP addresses. This is my IP address for this system I'm running on now. 192.168.1.182. Yours will be fairly similar. Okay, and we'll talk how it gets it and what we basically do with it in a little bit. But the important thing you need to realize is that for IP addressing, it's a fundamental concept of our networking. Okay, because the addresses we need to know, think of it as a postal address. We need to know where we are posting data, where we are sending things through to. So it enables networks to communicate over a local area network. So if I want to communicate with a printer, I know the IP address of that printer. So my data doesn't go to every device on my network. My data goes into the router, and the router says, or into the switch, and the switch says, that IP address belongs to that printer. I will pass that data to that printer. So that's the basics of it. Now, there are currently two systems out there. There's IPv4, which is the one we'll focus on because it's much easier to understand. Understand? It's the same concept. The difference is the number of numbers I'd have to read out when I talk about it, rather than IP6. You'll understand in a second when I do this. So IPv4 typically is 32 binary numbers represented in decimal. So the example there, 192.168.1.1. Okay, there's an approximately 4.3 billion unique IP addresses. Wow, that's loads. Okay, so IP4 addresses can be classified as public and private. Excuse me. Gosh, I should have paused that. And they have what's known as a subnet mask. Give me 2 seconds. Sorry, my apologies there. Now, Kaplan basically points out a very valid point, but we are 8 billion people. How many devices do we actually have? Loads and loads. But you've got to remember, on the World Wide Web, there are only allocated 4.3 billion unique external IP addresses. I then have my own internal IP addresses. So in theory, there is an actual limit to the size of my local area network, which is 4.3 billion devices. Someone can buy me a house, I can put that many devices in, I'd be quite happy. Now, the way that it actually works is this is where we talk, Kaplan, about the separation between an external and an internal IP address. I won't talk directly about it now because we do hit it in a second. But bear that in mind. Hold that thought, Kaplan. So IP6, so IPv6, and indeed this harks back to what Kaplan says. Hold on, 8 billion. We need more. So years ago they kind of went, yeah, we do need more. So went to IPv6 became available. Okay, it's a 128-bit hexadecimal number represented in groups of 4 hexadecimal digits. Now you're going to understand why I'm not doing with IPv6. It is just an address. Think of it as just an address. I would hate to have to stand here and read out IP addresses by going 2001 0DB8 85A3 000 A2, etc. That would be a nightmare. So 192.168.1.1 slips off the tongue a lot better. But those two addresses are interchangeable. Okay, so they are just a single address for the same device. And indeed, to demonstrate that, this is my IPv6 TP address. Oh, that's my address, isn't it, up there? Okay, so when I get allocated an IP address, I actually get allocated both because my switch, router, the HCP server, which we'll talk about later, gives me an IPv4 and an IPv6. So as I say, so coming down is this massive IPv6, which a lot of people are starting to using. So that's approximately 340 unidecilon unique addresses. Okay, so that's low. So Cablan, I think we're okay for a fair few years now. So how does it actually work? Remember I mentioned the switch and the router can sit in a particular location. We have what's known as subnetting. So whenever we talk about IP addresses, we will always consider subnetting. Now, the default and the main one we think about is if you look at the red text there is my subnet 192.168.50. That's my subnet. Don't worry about the IP6 subnetting at the moment, Alan. Try and keep it easy, shall we? That's my subnet, and my host is .20. So that's my location on that subnet. Now, the normal default with a router and a switch is that any device can normally talk to another device that is on its same subnet. So any device that has a subnet 192.168.50 on my local area network that plugs into a switch that has a physical connection going between the two, my host.20 can talk to my host.22, my host.23, my host.24. Those can naturally all talk to each other. That tends to be pretty much the default. Now, if we want to talk to something outside of our subnet, you can see the example there. We've got two different subnets there. So my LAN 1 subnet will give me IP addresses between 1 and 254. It has to go via something that is intelligent, like a router. So if my LAN 1 wants to talk to a device on my LAN 2, could be a separate floor that it's on, and wants to talk to a device on 10.10.1, that subnet, then the router must know about that subnet, and the router will control the traffic. It will route the traffic, and that's the idea. Anything the router doesn't understand, or when you ask for an IP address that it doesn't have a table for, it will throw out to the internet and say, the internet, do you have this particular device? Do you have this particular IP address available? Does that make some sense to people? And in terms and consequence, if I want to speak to LAN 3, again, my router must know that LAN 3 exists. And it must know the IP addresses and the subnet for it. And it will then say, yes, I can pass LAN 1 to LAN 3. Or it says, no, you can't. So for example, here, my LAN 1 may be able to talk to LAN 3 and LAN 2. But if my router wants to stop LAN 2 and LAN 3 talking, yeah, perfectly happy. It can stop that happening without any problems. And you can route it down to individual devices, but generally we talk along the lines of subnets. Wow, that's a big boom, isn't it? Does everyone get that concept? This is one of the fundamental concepts we need to understand, is that IP addresses have subnets and host IP addresses. So we can see in my example, clear, that's good. Sebastian says clear. So you can see in my example, excuse me, this is my subnet, and this is the IP address that I've got. So that's my host IP address. Beautiful. I like the fact that people are saying it's clear. Again, this is the stage you want to be asking questions. If you don't understand this concept here, it's not a simple concept. I nearly said that. If you don't understand this rather complex concept, then when we move on to some of the more advanced networking, it can be a little bit struggling. Great stuff. Now, how do we control subnets? And the subnet mask. Yeah, we're coming through to that, Marcos. So within subnets, so subnets basically allow us to divide network. That's the whole that's the whole point of IP addresses is we can now work them into subnets so we can divide things and control who can talk to who really easily. So each subnet will normally have a subnet mask, and that subnet mask defines how many IP addresses are in that subnet. Now I use the really simple one, which is what's known as a /24 subnet. Okay, that means it produces a range that will have all of those IP addresses in it. Now we can reduce that subnet by basically putting a different range on it. And these are basically broken into what's known as CIDRs, which is a classless interdomain routing. Wow, that sounds really horrible and complicated. We don't need to think about it mainly. Most of our IP addresses that we deal with on our LANs are with a /24. So that means when we notate this, we will say, for example, here, our IP address range is 192.168.1.0/24. And that means I can use the IP addresses from 1 to 254 on that domain. Now, when we talk about some more advanced stuff, we talk about different CIDRs. So we may have a CIDR that is a, trying to think of an example, a /16. I think /16 basically reduces that number down to 4 IP addresses, but I've probably got that totally wrong. So we'll go through that in more details. And we do that when we start talking about the advanced sessions. But within 90% of local area networks, we are simply dealing with the CIDR /24, and that means we're dealing with 254 IP addresses. Good. Can I see a thumbs up from everyone who thinks they understand that? Perfect. Sebastian, Maximilian got it. Well, I wouldn't mind seeing a few more thumbs up there so I understand that you've all got it. Cablan. As I say, if you are struggling at this point and think, oh my God, what are we talking about? Then yes, please put your hand up. Good. Okay, what I'm gonna do is we're gonna have a 10-minute break for you to get a coffee and a comfort break at this stage. And you can mull that idea over. If you don't understand anything, come back from the break and ask the questions, because that's what we need to be doing at this stage. Good stuff. Let's see what boogie and music we can bring up. Welcome back, everybody. Well, I hope you had a chance to get a little bit of a comfort break, pancake or whatever it is you were on the way to get. And let's have a little look at things then. So anyone come back with any questions about the networking and the things we've done with IP addressings? If not, I will drop onto a Kahoot quiz. You're not playing so well this one, are you, Paul? Let me see. So Max, right at the top. Let's see how we can go on here. Everyone ready? Thumbs up if you're ready for your Kahoot quiz. Sebastian, Marcos, lovely. Maximilian, Luca. Oh, look, Paul's not ready. Never mind. Okay, a couple of you typing there. All right, okay, so ready? We're going to hit the button. True or false? Oh, a network protocol can be compared to a language. Bit tricky of me. I don't think we've discussed this one yet. Let's see if anyone gets this one right, and then we'll have a little conversation around it. True. Network protocols can be happily compared to languages. And for those people that don't know what protocols are, it is literally, we'll go into it in 30 seconds. See, Precious is typing there. See a few of you typing. I'm just going to let you catch up. That's fine. That's fine, Precious. It's only a fun game, isn't it? Okay, so what is a MAC address? So we talked about IP addresses. Yes, we know we can talk about IPs. Yes, that's what they all are. They're nice little addresses, 192.168.1.50, currently an IP address. So where does a MAC address come in? So a thumbs up for anyone who's heard of a MAC address before. And we're not talking about the PCs that are produced by Apple. So Marcos, Alan, yep, you both heard of MAC addresses. Paul Bird, fantastic. Sebastian as well. Okay, so we've got a couple there. So MAC addresses are unique identifiers. It's really important we focus on that. They are unique identifiers for the network interface controller, currently known as a NIC. Okay, we all have NICs. Our NIC is a Wi-Fi connection. It is the physical port that we're plugging into our network cables. So plugging those in, and they are unique. You will not get the same MAC address in the world. So the MAC address 00:0A:95:9D:68:16 is only available on one device. They are 48-bit addresses, 6 bytes, expressed in 12 hexadecimal digits, usually separated by a colon. So that MAC address is only available for that one device. How do I find out my MAC address? Well, within the Mac OS, you can basically use the Apple menu at the top left-hand corner, select your system preferences in your network, and that'll basically tell you what your MAC address is. Within Windows, you can go to the command prompt, like I did, basically find my IP address. And that will basically give me my MAC address. Where is my MAC address? Oh, I lost it there. Ah, there it is. Okay, so that physical address, that is the MAC address. Wow, Dave, why have you got so many different addresses? Okay, because this is my Ethernet adapter one. Okay, but I've also got a wireless one, so there should also be a wireless MAC address. Wireless, with a wireless MAC address. Okay, and I've got a variety of connections because that's what I mess about with. So single MAC address is a individual item, an individual NIC, network interface card, an individual one. So if I have a server that I have 5 network cards in, that server essentially can be spoken to with 5 different MAC addresses. So how do we keep the MAC addresses separate then? So the MAC addresses are basically assigned. Okay, so they are given. There's a big company up in the big wide world, like IEEE, that manages the registration for MAC addresses. And they tend to give them out in particular bundles. So, for example, HP will have a big bundle of MAC addresses, and they get allocated them and say, these are the MAC addresses you can use for all your network cards you ever produce in manufacturing. Dell will have a set, Toshiba will have a set, etc., etc. So that's how they're done. Even to the point of virtual machines. If you run a hypervisor, which is a virtual machine controlling system, they will be given MAC addresses by these particular governing bodies. So you should never see the same MAC address anywhere. Why do we care about MAC addresses? Okay, this is where it gets a little bit funny. So let's have a look at the network modeling. So there's two famous models that we basically use. There's the OSI model, which is the Open System Interconnection model. It deals with layers. And now we talk about the different layers that we move through. So there's layers in the OSI model, and it's probably better if we show you the picture in there. And they interact, and the data will travel down the layers like a cheesecake, and it'll come out the other side and get interpreted the other way. The second model is TCP/IP. Now they're not so different. Okay, basically TCP/IP model basically works on the OSI model. OSI basically came up and they said this is a standard way that every single network is going to talk to each other. Now when we use the TCP/IP, that was TCP/IP literally coming along going, we like the OSI model and we're going to handle it this way. Something like X25, which is another networking idea. X25 is used to be a bit of a competitor to TCP/IP, but it isn't anymore because it's too small fry. That uses its own model based around the OSI model, so it does the same thing. So this is how our network communication works between devices. So you can imagine you're sat there at the top where the data basically is. That's your user. This is you basically doing things. That's your application layer. So if I want to send some communication to another system, I will pass my data to the application layer. And then the application layer will basically provide application-specific functions. It will do a variety of things like in there. And then it will pass it to the presentation layer. Now, the presentation layer then deals with the data transfer and encryption. So that's where it becomes encrypted and deals with things such as translating the data format, handling data errors and encryptions. That will then pass it to the session layer. Things such as manages for the terminations and successions on there. And then that will go to the transport layer. And the transport layer will again look at end-to-end communication services. Then it goes down to the network layer, and the network layer focuses on routing. So this is where we're talking about IP addresses. So at that layer, it understands IP addresses. Then the network layer passes it on to what's known as the data link layer. Now, the data link layer doesn't really understand IP addresses. It only understands MAC addresses. So my network layer has passed it an IP address. The data link layer goes, that IP address is that MAC address. And then it will use the MAC address because that's an absolute location. And then it passes it to the physical layer, which is our cables. And our physical layer is really responsible for the cables, Wi-Fi, etc. That then basically is responsible for transmitting the raw data that we now have. So that then whizzes down the cable, which is the blue bit at the bottom. And then we do it all in reverse. So we unpack it from the data link layer. Our network layer says, oh yeah, I'm the right MAC address. Sorry, the data link layer says I'm the right MAC address. The network layer says, yep, that's the IP address I've got. Transport layer then unpacks it a bit more, session layer, and then presents it basically a copy to the application layer, which is where the other person sees it. So that's how the OSI model works. So that's how all your data is. So when you press a key or when you send a command, it gets packaged up by each of these different layers doing a different thing, and then unpackaged in reverse to the other end. Does that sound sensible? Okay, so what we don't have to remember all those details. What we need to remember is that there is an OSA layer, OSO model, and it's 7 layers, and potentially what each of those layers are. So TCP/IP, wow, hold on, they just kind of went, we're going to make it a little bit easier. So we kind of stripped the layers out of it to make it a little bit easier for us to basically manage. So we still have our application layer in there that basically deals with the fundamentals of user level communication network applications. That then passes to the transport layer, which is where we talk about protocols. So we can talk about TCP or UDP protocols. And then that passes it onto the internet layer. And that does the IP or ICMP. Oh, horrible acronyms, aren't they? And then it goes into the data link layer, which essentially is the network, follows by the network cable. So it's a little bit simpler. 4 layers in there instead of the 7, the OSI model. But it does exactly the same thing. Every piece of data is passed from one location, one layer, to the next layer where it does something else. It might add a bit, might encrypt the data, might agree the transition for the data, and then passes it on to the next layer that then does something else. Sort of an in and out approach. Thumbs up if everyone understands that. Well, wave a hand if you don't. That's the big thing, isn't it? It's only a concept, really. We kind of show you this because it's kind of a nice to know, a need to know thing. People ask you some weird questions about networking. To be totally honest, I spent the first 15 years of my career doing networking and IT management. I didn't even know what the OSI layer was. I didn't have a clue. It didn't matter. I knew that if I had an IP address and I had to route it there, well, that was great. I routed it. I didn't care that it went through 7 different layers. Didn't even use it. Great stuff. Okay, so let's swiftly move on to network protocols. So what is a protocol? We've already said it's a language. Think of them a bit like languages. They very much control the data formatting and structure. So it's how that data is wrapped. How is it packaged? Is it packaged by an IP address at the front? Is it packaged by a MAC address at the front? Is it encrypted? So it deals with the encapsulation and the encrypting. Deals with my address routing. So again, our IP address and MAC addresses is in there. And it deals with our error handling. Is there any error handling? UDP has no error handling at all. It's very much a fire and forget. Okay, and it also deals with security. So the roles of essentially the protocol in communication, as I say, it's a bit like a language format. When I construct a sentence, I know I'm going to start with a capital letter in my protocol. Any name is also going to be capitalized, and I'm going to end with a form of punctuation, an exclamation mark, a question, or a full stop. That essentially is my protocol. Now I'll put that protocol into English. That's great. But if someone speaks to me in French, because that's a different protocol, I won't understand it. So protocols need to match each other. So if I'm talking in English, the person at the other end must understand English. So it's like a protocol. So as I say, network protocols are basically a bit like ensuring that data can be transmitted reliably and efficiently across networks, including encryption, if there is encryption in the protocol. So it defines the structures and behaviors of networks. Manages how they handle errors. So is there error handling? How does it handle the error handling? And there are different layers of protocols in network stacks. Don't concentrate too much on that. That kind of confuses little things. But there are different layers that basically get involved. As we saw with the TCP/IP, you can see that the IP part of it is down in layer 2, whereas the TCP is in layer 1. So here's a couple of example protocols. Okay, TC is the transmission control protocol. That's the big wrapper that sits around all these. IP is the internet protocol. We love the internet. Without TCP/IP, we wouldn't have the internet. Well, we probably would. Someone would have thought something different. But where do we use things like HTTP? Someone tell me where we use HTTP? See a couple of you. Web searching. Yes, so that's the protocol that basically deals with hypertext transfer protocol. It's used for web browsing. This is how we understand web pages because they're passed to and from us in a HTTP protocol. FTP, which is a file transfer protocol. So this is where we can use a particular protocol for transferring files to and from servers across the network. I can use commands such as FTP put to put files into particular locations. Really good for building your web pages. We can put data into those as well via that. SMTP, which is the mail protocol. We covered that the other day, didn't we? Well, remember, we said that SMTP was the mail transfer protocol between mail servers. So they've all got to speak the same language, otherwise it will come out as gibberish. So you don't have to remember all the protocols, you just have to remember that there are lots of different protocols that are used. Any questions about network protocols? We're going to quickly summarize it there for us. So network protocols basically serve as a foundation for the data communication, okay, allowing us to transfer data from one location to a site that will understand it. If I talk to that in a different protocol that it understands, the data will just get garbaged and it'll get rubbish and it'll get dropped. Good stuff. Okay, I'm liking this then. So how do our network services work? We're going to go through some of the fundamental network services just to understand things. One of our key network services that we use is DNS. And we're going to cover the very light end of DNS. DNS, which is domain naming systems or services, depending on which company you learned it from, converts domains into IP addresses and IP addresses into domains. So if I'm on my web page and I'm searching for google.com, how do I know where to go? Well, DNS basically sorts that out. And it does it in a very simple way. So a quick example I can use here. I'm going to ping google.com, all IP address 6. I'm going to read those out. So you can see that has basically looked up google.com and it's found out it is on that IP address. So it's converted the name google.com into an IP address. That's DNS. How does it do it? Well, it basically goes through a lookup and it looks at different DNS caches on the systems. Now, every device you have, laptop, mobile phone, smartwatch, potentially PC, will have its own local cache. But its local cache only consists of those things that we've already looked up. So it's like an address book. If I've got a little address book, I've got 10 names that my 10 friends. I will know those 10 friends because I've got it written down on my address book. But if I want to speak to Dr. Martin, I don't know his address. What I will do is I will phone up one of those 10 friends and say, do you know Dr. Martin? And if he doesn't know Dr. Martin, he will phone one of his 10 friends. And one of his 10 friends may then know Dr. Martin. And when someone finds out and puts their hands up and says, oh, I know Dr. Martin, that IP address comes all the way back down the line to me. And I then have in my cache, I've written in my little book again, Dr. Martin, IP address. And that's called DNS resolution. Anyone got any questions about DNS resolution? So I guess go on, I can see Sebastian typing. I was going to ask a question myself then. Okay, so it kind of forms a chain. So it's a chain of event. Now, I know that I've got a DNS on my one. So where do I first look to find the next DNS? So where am I basically looking? Anyone able to answer that one? In your router DNS table. Well done, Alan. Now you can see there, my router is on 192.168.1.254. That's my router. So if my local DNS cache doesn't know about it, the first thing I'm going to ask is my router. And my router may say, I don't know about it. It may say something else. So if my router doesn't know about it, where does my router next go out to? Who sold me my router? Firewall. Oh, yep, router, firewall, ISP. Ronald, you get a bag of sweets. Alan, you've already got one for router anyway. So your ISP, so it goes out to my internet service provider. So my router, if you ever look at the configuration on your router, it will give you 2 DNS servers. Okay, those 2 DNS servers are likely to be the ones that are local to the ISP. So it will check that. So as you can see, I'm spreading out now. I've checked my cache. I then check the cache that's basically on my router. Now the cache on my router, of course, has got all the correlation of all the DNS searches that everyone connected to that router has done. So my son, my daughter, my girlfriend, etc. So all those people have basically used that to look up different things. So that's why that's a bigger cache than I've got on my local machine. And then, of course, my DNS, my router will then go out to my ISP. And you imagine the amount of queries that are going through your ISP. Well, yes, so they probably know where everything is. And that basically just comes back to me and propagates my system. Well done, Ronald. Well done, Ronald. Now, what keeps it fresh and what keeps it live and exciting, live and exciting, that's the wrong way to put it. What keeps it fresh is that every time a DNS record gets written, either to my router or to the ISP or to my local cache, it has what's known as a TTL, a time to live value. And the TTL basically says this DNS will be valid for X number of hours, X number of minutes, X number of days. So you can basically set that value. It's normally set somewhere between 12 and 24 because you do not constantly want to wipe it. And what that means is when I look for Google, it will remember Google for example, 6 hours. And then after 6 hours has expired, and I go and try to find Google again, it will then go, I've wiped it off my cache, I'll have to check with the router. And the router will go, I've wiped it off my cache as well, I'll have to check with the ISP. And that keeps things fresh. So that means if someone like Google moves their company location and changes their IP addresses and gets new IP addresses, it means we don't get panicked. And we only have a small period of about 6 hours where we're looking at the wrong IP address before everything gets forgotten and then we're re-asking. So that's what TTL, not time to live, basically does for us. So I think the best way I've looked at and basically describing DNS is simply as an address card. Like I said, I've got my address book. I ask my friends. The TTL is me every 6 hours. I'm just ripping out the address book, throwing it in the bin, and starting a new one. So it's done per IP address name rather than actually per address book. Is that clear for everyone? Perfect, Sebastian. I like Sebastian. Thank you very much. So as it says there, TTL is normally the lifetime of it. It's normally between 12 and 24 hours. So of course you've got to imagine that this is all going to be managed by someone because we can't have multiple people using the same IP addresses. So it tends to get managed by ICANN, the International Corporation for Assigning Names and Numbers. Great name, isn't it? What a fantastic company to work for, ICANN. So they will allocate it. And you will find that your ISP, your internet service provider that you go through, has a whole load of IP addresses it's been allocated. Just like the hardware manufacturers get a whole load of MAC addresses, they've kind of got a big pool of IP addresses they've got given. So the basic fundamental thing to remember about DNS, the simple part of DNS we're covering today, is DNS is designed to convert real names, google.com, to IP addresses. And that way IP addresses can be routed across the internet because it's an internet protocol address range. Good stuff. Any questions? I think we're doing pretty well. We're cracking through this, loving it. So DHCP, I've got an IP address. Where did it come from? Okay, yes, I can allocate the IP address myself. I can go onto my hardware device. I can go, well, I want this IP address. Okay, but why would I do that? Imagine trying to be on a network system and attempting to manage and allocate 254 IP addresses around your company. How are we going to make sure we don't get a duplicate? And I'm going to have to go around every single new machine and go, okay, we need to get that one an IP address. Okay, so we don't do it like that. We use a service which is called DHCP. So we all have DHCP servers available. Bonus in the live chat for somebody who can tell me where their DHCP server is. No one know where your DHCP server is? I see Alan typing. Sebastian, let's see if Sebastian can beat Alan to the punch here. Oh, Sebastian's in there. In the router. My God, our router's doing everything, isn't it? Yes, it is. Does our DNS, it does our DHCP. Wow, it's a fantastic toy, isn't it? Yes, so okay, so it basically goes to there. So when we plug a network device in, or we connect via Wi-Fi to our hub, essentially like that, what happens is Dora steps in. Now, Dora is not just an explorer, a Spanish explorer with a guy, little monkey called Boots, who runs around with them. I get that from watching it too much with my kids. Dora is essentially a protocol that basically works. So it works on a discovery. So the client literally says, this is my laptop, pops up and says, is there any DHCP servers out there? Hi, can I speak to a DHCP server? My router, or a server, if you're in a bigger business, it might be on a server, literally will pop back and say, oh, mate, I'm a DHCP server. Here's an IP address you can have. So it gives me my 192.168.1.20. My client, my laptop, then says back to the server, says, oh, I've got that one. Are you okay if I keep it and use it? And the server then acknowledges that and says, yes, you are now registered. You can continue to use that. Now that feels a little bit long-winded. Why have we got 4 processes going backwards and forwards? We've got 4 processes going backwards and forwards because it's possible that we've got more than one DHCP server. Big companies, you might have one per floor, you might have one per IP address range. Why would you only have one? What happens if that one falls over? Where does everyone get their IP addresses from? So redundancy, I'll probably have 2 DHCP servers running on my network. And the way that it works is that the reason it's done like this is because we get the discovery in the offer. Okay, that's great. The client's now got one. He's got to confirm that he's using that one. What happens if he got offered 2? If he got offered 2, he's got to go, oh, I've got to pick one. So he picks one, tells both servers that he's using that IP address. And then the server that offered him the one that isn't available or he isn't going to use now gets freed up and will get allocated to someone else. Fastest wins? Yeah, sure. It is very much a case that the fastest wins. So your client will basically grab the first one it gets offered from a DHCP server and it'll go, yep, that's good. I will have it. A bit like Kahoot, isn't it, Alan? Paul will tell you all about it. So that's how IP addresses are basically allocated. Yes, as I said, we can allocate them manually. By basically going into our network configuration tool and managing those. That's what we cover with the basics anyway. DHCP server. Okay, as you can see, it is my router. Any questions about DHCP and our friendly Dora who's going to give IP addresses out? Stop arguing, you two. The DHCP server will also do several things. So when it gives you an IP address, does the server have a specific IP address? The server doesn't have to have a specific IP address. When you talk on the network and you're waving your hand going, give me an IP address, DHCP server, that is a broadcast. So every device on the system that knows about DHCP will receive that message. Loads of devices will simply go, that's not me, and ignore it. That's not me, I ignore it. A DHCP server will wave a flag and go, oh, that's me, I've got this one, and it'll give you an IP address. So the DHCP doesn't have to have any particular IP address. It just has to be on the same subnet for it to pick it up. Does that answer that one, Alan? Love those questions. 10 minutes. What am I doing for 10 minutes? Looking at the time. The DHCP server is allocated an IP address. DHCP servers are normally on a static IP address. We'll talk about DHCP server ranges later when we do the advanced settings. Okay, we won't talk about it now. Just remember that's an easy way for getting the DHCP address. Because we've only got 2 hours. That's why we break it into 2 sections. So NAT, what's NAT all about? NAT is network address translation. So we talked about internal addresses and external addresses. This is really where NAT comes in. Within my local area network, I've got all my lovely addresses, and they're my addresses, and I can do pretty much what I like about them. When I go out to my router, I have what's known as a public IP address, and I will have a single public IP address that anyone who talks through my company will have to talk to. But what I've got to do is I've got to translate that address. So if my system on 192.168, I'll tell you what, my system on 192.168.1.25 talks out to the internet, the router will know that conversation started from my IP address. The internet will still only see me as 86.24.215.104. So the response will come back from my web query. I may be looking for some images. So the response will come back from that web query and it will hit my router. And my router will say, I know where that request came from because I've got it in my network address translation. So it will say that information was requested from my IP address on the .25 and it will pass it back. So that's what NAT does. So that means from as far as outside is concerned, they cannot see my local area network. They do not know my internal IP address. They only know the external IP address. And that essentially is our first barrier to prevent people getting onto our systems. How does that sound? Right, fantastic. That sounds great, doesn't it? Okay, so what is my IP address? There's a question from Alan there. Okay, as NAT is or data more or less visible to the external internet? No, NAT isn't available to the external. NAT is basically handled at our router, firewall, switch, whichever one happens to be dealing with it. So anyone from the internet will not see that the request was made from 192.168.1.25. It only sees the request made from 86.24.215.104. So it doesn't know the internal IP addresses. Here's a good example. Oh. So here you can see my external IPv6 address and my external IPv4 address. So this is what I talk to the internet and you guys from. So as far as Zoom and everything else is concerned, that is my IP address. And my firewall basically does the NAT at this end. Any questions in there? I can see Chris typing away feverishly. I should probably warn you, this is one of the lectures that we cram so much into, we may overrun just slightly. Chris, I can see you typing again. Much rather handle the questions now than later. Okay. Probably my system just keeps popping up and saying Chris is typing. All right. Okay, so let's have a bit of a Kahoot then. Let's finish off some of those Kahoot questions for us. Let's see who's in the lead. And let's see who's going to have to play catch up. So Sebastian's in front, RD, Max, M, Zachariah. Ready, steady, go. Another quiz then. Multi-select. Which one of these are valid IP4 addresses? What's a valid IP4 address? Bearing in mind, the numbers can only go up so far. Oh, well done there. So the blue one isn't, because it is above 255. Remember, our IP addresses will only go as far as 255.255.255.255. We don't ever use that IP address normally, just as we don't use zeros. So we don't use 0.0.0.0. So whoever took the red and the yellow, well done. The green one is an IPv6 address, so it's not an IPv4. Good stuff. Let's see how that changes the thing. Max is shot to the top. M is right up there as well. Another couple of questions coming up. A subnet allows the network administrator to divide network into smaller sections. True. So it allows us to divide them up. We allow 255, 254 essentially devices. So that's as big as it gets. We can make it larger and we can make it smaller, but it allows us to basically break it up into controllable modules and controllable sizes. Well done. Max is still at the top. Let's see how we go. We've got a couple more questions to go. A DHCP service converts real names into IP addresses. Oh, so I snuck that one in there. DHCP gives us our IP addresses. DNS converts them into real names. See if that separated the wheat from the chaff. Paul B, well done. True or false? My internal IP address is the same as my external IP address. Cool. So your internal IP address is normally totally different from your external IP address. Your internal one you get from your DHCP server, and your external IP address you get from your ISP. So your internet service provider will give you that IP address. I won't tell you, I won't phone you up and go, this is the IP address you've got. They allocate it onto your router, firewall. Good stuff. Right, and our final question from today. All my laptop has a local DNS. All our laptops have a local DNS. True, yes. All our systems basically have a local DNS cache that we look at first. So before we see the final results, let us just finish off a small piece we have on basic network security. Why do we have IP addressing? Why is it so important? What do we deal with? Remember, our network is vital. We won't say this enough. Our network needs to be secure for confidentiality, to make sure no one gets unauthorized access to our data, to maintain integrity, to make sure that things aren't changing, and make sure it's available. So we need to make sure our availability is good by having redundancy stuff. So a second set of switches in there does us good. And we work with both authorizations, authentications, and accountability to make sure we can trace what happens, who made a change, who requested these items, so it's all traceable. So the basic way that we do protect ourselves is we have firewalls. So firewall basically acts as a first barrier. We then have what's known as intrusion detection systems. So these are special systems purely designed to detect if something is going wrong. So look for malicious behavior on our systems. And then we have encryption. So we've got to make sure that we basically do some encryption to make sure that the stuff is secure across our networks, so people cannot get onto them. But we can quickly chat about some common network issues. We do a section at the end that basically deals with our network troubleshooting. We're just going to quickly run through a few common issues. So connection problems, devices unable to connect to the network or limited no access. Things such as cables. I constantly say, check the cable. Slow network speeds are basically related to network performance. Is it being overrun? We'll talk about this a lot more. DNS issues. If we're unable to get to a particular DNS location, is our DNS correct? Do we need to have a little flush of our DNS and reload our address book in the system? A typical example of an intermittent connectivity could be an IP address clash. If I've got another device that is stealing my IP address, has a manually assigned one, and gets allocated the same IP address, we will end up with things such as IP conflicts, where the devices receive conflicting IP addresses. That means we fail to get the connections. And of course, common issues of security concerns. So suspicious activities, malware will slow us down and will cause issues with our network speeds. We kind of went through a bit of this when we did the basic troubleshooting, so I won't loiter on it a lot. Basic troubleshooting is very similar across the board. So we need to isolate the issue, use some troubleshooting tools such as ping, ipconfig, and traceroute. And we cover those when we do the advanced networking and the troubleshooting in a couple of days. Physically check the NIC, physically check the cable. I ran cables in one office, and unfortunately they were on the floor, and we had people that were simply rolling their chairs over the top of them. Strange enough, the cables got absolutely knackered, and they weren't getting any connections. So watch out where you run the cables. So before we reveal the winner of Kahoot, the lesson conclusions. Okay, so we've learnt about the basic terminology. Okay, we've learnt what an IP address is. We're focused very much on IPv4 simply because it saves me chatting for too long over those different numbers. But consider them to be exactly the same thing whenever we replace them. So we know a LAN is a local area network, a WAN is everything, a connection of lots of local area networks, and a MAN is more metropolitan, more within that town area. We've had a quick chat about some network topologies, the pros and cons, and we've recognized some key network protocols. We don't need to go into massive details about some of the protocols, but it's definitely